This new project that I'm in charge of really has me stumped. Do you mind if I think out loud for a bit, Winston? Thanks. I have a ton of data about websites, and I want to be able to search through them by which pages have links to each other. There's an issue, though. I can't get a clear mental picture of what that would look like, and I don't know which data type is best for modeling connections between web pages. You think I should use a graph? What's that? Right. That's a lot of technical mumbo-jumbo, but I gather a graph is a data structure designed to show relationships between objects. Sounds great. I can't wait to learn more. Okay, so what does a graph look like? Ah, wait, no. I've been conditioned to think of a graph as a chart that shows trends, like a line graph or a graph of a function. But that's not what we're talking about here. Let me try again. Our definition of a graph looks more like this. The purpose of a graph is to show how different things are connected to one another. It's also sometimes called a network. A graph is similar to a tree in many ways. For starters, these are called nodes or vertices, and these lines over here are called edges. In fact, a tree is just a more specific type of graph. It's just like a binary tree is a type of tree, and a BST is a type of binary tree. Here's an example of a valid graph, where you can really start anywhere and you'll follow some path back to the start. Since cycles like this one are possible, graphs don't really have a root node like trees do. Graphs are really vaguely defined, but we should keep it that way. As you've probably come to expect, we need to keep it vague so our definition will encompass all of the different use cases for a graph. For example, I would love to say that nodes are the parts of graphs that store data, and edges are just the connections between them. But edges can actually store data too. Since graphs can seem really abstract at the start, let's make them more concrete with some examples. Let's imagine this graph as a social network. This node can be me. I can draw the rest of the graph like this. Here, it's clear that nodes are people, but the edges between the nodes could be describing any connection between us. Maybe it's people who've met each other. Here, two nodes that are connected by an edge, sometimes called adjacent, have met each other in person. This could be a graph of people who've lived in the same city at the same time, or people who've worked on a project together. The nodes could contain any amount of data, like each person's full name, where they live now, their birthday, etc. As I said before, edges could contain data too. Edges often contain data about the strength of a connection. For example, these edges could show how many times in the past week we talked to each other. Okay, let's think about a new example. Let's say this graph is my travel plans for a big trip. I'm going to fly from San Francisco to Tokyo, then Kuala Lumpur, then Delhi, then back to KL, Tokyo, and SF. The edges could contain no information, or they could contain how long the flights are. The information I decide to store will depend on what I'm using this graph for. Graphs have some additional properties that make them useful for modeling various types of data. Edges can have a direction, meaning the relationship between two nodes only applies one way and not the other. Directed graph is the term for a graph where the edges have a sense of direction. For example, if you're using a graph to represent travel plans, a directed edge can be used to show which city you start in and which you travel to. Often, one node will be the start and the other the end of the relationship or action taking place. You might describe the edge of a graph as the first node, a verb, the word to, and the other node. Here, it's from SF, travel to Tokyo. If you make a round trip and travel through the same two cities going in opposite directions, you might have two edges between the same two nodes, one representing each direction you travel in. An undirected graph has edges with no sense of direction. For example, if you have a graph of people and edges are drawn between two people who've met before, directed edges might be unnecessary. I previously mentioned that graphs can have cycles, but trees can't. A cycle happens in a graph when you can start at one node and follow edges all the way back to that node. Cycles in graphs can be really dangerous when you're describing algorithms. You might write some code to travel through the nodes in your graph, but if you have a cycle, you might just go through the same sequence again and again and again in an infinite loop. You often need to make sure the graph you're taking in as input is acyclic, meaning it has no cycles. One type that shows up often is a DAG, or directed acyclic graph. It's really just what it sounds like, a directed graph with no cycles. Another important property of graphs is connectivity. That term has a specific meaning in the study of graphs called graph theory, but let's define what it means for a graph to be connected first. A disconnected graph has some vertex that can't be reached by the other vertices. A disconnected graph might have one vertex off to the side with no edges. It could also have two so-called connected components, which are connected graphs on their own but have no connection between them. Thus, a connected graph has no disconnected vertices. There's also a metric used to describe a graph as a whole called connectivity. Let's look at two different graphs and say they're each describing a different group of friends. When looking at these two graphs, the one on the right looks like a much stronger friend group. There are overall less people but more connections between them. In the left group, I could remove one connection and the whole group would be destroyed. This is the principle behind connectivity, which measures the minimum number of elements that need to be removed for a graph to become disconnected. Depending on the information in the graph, you can sometimes use connectivity to answer the question, which graph is stronger? Graphs can be functionally the same, but built in a handful of different ways. If you're using an object-oriented language, you could create vertex and edge objects and give them each properties like name, strength, ID number, etc. A vertex could have a list of edges it's connected to, and vice versa. However, operations that traverse graphs can be more inconvenient if you need to search through vertex and edge objects. There are several ways to represent connections on simple graphs that only use lists. One example is an edge list, which is precisely what you'd think. It's simply a list of edges. The edges themselves are represented by a list of two elements. Those elements are normally numbers that correspond to ID numbers for vertices. So, in the end, this list is just showing two nodes that have an edge between them, and an edge list is the list that encompasses all the smaller lists. Because our edge list contains a list of other lists, it's sometimes called a two-dimensional list or 2D list. If you had a list of lists, that would be called a 3D list, and so on. An adjacency list is another way to represent edges in a graph. In an adjacency list, your vertices normally have an ID number that corresponds to the index in an array. In your array, each space is used to store a list of nodes that the node with that ID is adjacent to. For example, the opening at index 0 represents a vertex with an ID of 0. That vertex shares an edge with one node, so a reference to that node is stored in the first spot in the array. Again, our adjacency list is two-dimensional, since it's a list that contains other lists. Lastly, an adjacency matrix can be used. In computer science, a matrix is essentially a 2D array, but the lists inside are all the same length. A matrix can also be called a rectangular array. When you look at it, it looks like a rectangle. The adjacency matrix is actually really similar to the adjacency list. The indices in the outer array still represent nodes with those IDs, and the list inside still represents which nodes are adjacent. However, these inner lists represent information in a slightly different way. Before, the list contained just the IDs of adjacent nodes. Now, the inner list has one slot for every node in the array, where node IDs map to array indices. If there's an edge between these two nodes, a 1 goes into the array. If there's no edge, a 0 is present. You might notice that the diagonal, or the place on every line where the row number equals the column number, is always 0. This value would only be 1 if there was an edge that started and ended with the same node, but we don't have any of those in our graph. You should also note that a single edge shows up twice in the matrix. For example, this edge shows up when the row is 0 and the column is 1, and also when the row is 1 and the column is 0. Which method of representation you use depends on what makes the most sense for you and what operations you'll be performing the most often. If you're looking at node degree, or the number of edges connected to a particular node, the adjacency list will probably be the fastest. As you've seen, graphs are great for modeling connections between elements. That's wonderful on its own, but graphs are really powerful because they're so easy to traverse based on connections. Graph traversal is a lot like tree traversal. Again, a tree is just a specific type of graph, so that makes sense. We have two basic methods for traversal. A depth-first search, where we follow one path as far as it'll go, and a breadth-first search, where we look at all the nodes adjacent to one before moving on to the next level. These traversal techniques often show up bundled into more advanced graph algorithms, so make sure you understand them before you move on. Depth-first search, or DFS, on graphs operates under the same principles as DFS on trees. Keep in mind that a graph search and a graph traversal are roughly the same thing. In a traversal, you look at every element, and in a search, you just stop traversing when you find the element you were looking for. Unlike a tree, there's no root in a graph, so there's no obvious place to start. You can begin with any node. First, mark the node you selected as seen. A common implementation of DFS uses a stack, so we can store the node we just saw on the stack. Next, you pick an edge, follow it, and mark that node as seen, and add it to the stack. As long as there are more edges and more unseen nodes, you keep repeating those steps. When you do hit a node that you've seen before, just go back to the previous node and try another edge. If you run out of edges with new nodes, you pop the current node from the stack and go back to the one before it, which is just the next one on the stack. You continue this approach until you've popped everything off the stack, or you find the node you were originally looking for. There's another common implementation of DFS that uses recursion and no stack. As you can imagine, you just repeat the same process of picking an edge and marking a node as seen until you run out of new nodes to explore. That becomes the base case, and you move back to the last level of recursion, which happens to be the previous node in the search. In this algorithm, we're explicitly visiting every edge and vertex once. Thus, the runtime is often written as this, which reads the number of edges plus the number of vertices. You might notice that we actually visit every edge twice, once to explore it and once traveling back through it. The runtime is technically 2e, but the approximated version remains the same. The number of edges by itself actually summarizes the runtime pretty well, but the v is added to account for the time taken to look up a vertex. That exact time varies depending on your choice of data structure, so be careful to base it on your implementation when asked. BFS, or breadth-first search, is actually quite similar. You're still visiting every edge and marking off every node. However, here you search every edge of one node before continuing on through the graph. Again, we start with the first node and mark it as seen, then visit a node adjacent to it. Once we mark that node, we can add it to a queue. Remember the difference between a queue and a stack, like we used for DFS. For a queue, we'll remove the first element we put in it, but for a stack, we remove the most recently added element. We go back to that first node and visit everything adjacent to it, marking each as seen and adding them to a queue. When we've run out of edges, we can just dequeue a node from the queue and use that as our next starting place. We look at every node adjacent to that one, adding each one to the stack until we've exhausted our options. It's important to note that when we dequeue, we're getting a node adjacent to the one that we started with. You can kind of envision a BFS as creating a tree out of a graph. The node that we started with becomes the root. The group of adjacent nodes is the next level in the tree. We need to continue adding nodes one level at a time. We finish off one level entirely before moving on to the next. And soon we're done with our BFS. The efficiency is still the number of edges plus the number of vertices. Again, we're visiting every edge and vertex during our traversal. One solution to the shortest path problem for weighted, undirected graphs is called Dijkstras' algorithm. Let's say we're trying to find the shortest path from here to here. We begin by giving all vertices a distance value. A distance is the sum of edge weights on a path between our starting point and whatever vertex we're on. At the end of the algorithm, this distance will be the distance of the shortest path. The distance value we start with is infinity. This is a placeholder value that will update whenever we discover a node and have an actual distance to store. The node we're starting with will have a distance of 0. A common implementation of Dijkstras uses a min priority queue, where the element with a minimum priority, or minimum distance in our case, can be removed efficiently. We store all of our nodes in the priority queue and use extract min to take out the minimum element, the only one with a distance of 0. From our starting node, we have several options. We will follow each edge and update the node on the other side with a distance value, which is just the weight of the edge. Now we're faced with a choice. Which node should we visit? We'll always pick the node with the smallest distance value, which means we run extract min on the queue. Because we always pick the node with the lowest distance, Dijkstras is often called a greedy algorithm. The philosophy for this class of algorithms is pick whatever option looks best at the moment, hence the name greedy. We repeat the process, visiting all adjacent nodes that are still in the queue and updating their distance values if we can decrease it at all. We keep going, extracting the minimum from our queue and exploring adjacent elements until the node we're looking for has been extracted from the queue or everything else has a distance of infinity, which means the path we're looking for doesn't exist. The basic runtime of Dijkstras is the number of vertices squared. Since in the worst case we visit every node in the graph once or twice, and every time we visit we need to search through the queue to find the minimum element. There are a lot of optimizations for Dijkstras. If the priority queue is implemented really efficiently, the runtime looks more like this. Hopefully you've gotten used to straightforward titles in computer science by now. If so, you might be able to guess that the shortest path problem is all about finding the shortest path in a graph. Early on, we talked about weighted edges, where the edges in a graph have some numeric value associated with them. The shortest path is the one where the sum of the edges is as small as possible. If we had an unweighted graph, the shortest path would just be the one with the fewest number of edges. The nature of the solution to this problem changes a lot depending on the type of graph. For example, the solution to the shortest path problem for an unweighted graph is actually just a breadth-first search. With a BFS, you start at one node and visit the closest nodes first, slowly moving out to more distant nodes until you find the one that you were looking for. Again, when there's no weights, you just want to find the path with the least number of edges.